Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 5, Conic Sections. Section 44, the polar system of a conic. Theorem 13. If P is a point in the plane of a conic, but not on the conic, the points of intersection of the tangents to the conic at all the pairs of points which are collinear with P are on a line, which also contains the harmonic conjugates of P with respect to these pairs of points. Theorem 13 prime. If P is a line in a plane of a conic, but not tangent to the conic, the lines joining the points of contact of pairs of tangents to the conic which meet on P pass through a point P, through which pass also the harmonic conjugates of P with respect to these pairs of tangents. Proof. Let P1, P2, and P3, P4 be two pairs of points on the conic which are collinear with P, and let P1, P2 be the tangents to the conic at P1, P2, respectively. Figure 58. If D1, D2 are the points P1, P4, P2, P3, and P1, P3, P2, P4, respectively, the line D1, D2 passes through the intersection Q of P1, P2. Theorem 8. Moreover, the point P' in which D1, D2 meets P1, P2 is the harmonic conjugate of P with respect to P1, P2. Theorem 6 of Chapter 4. This shows that the line D1, D2 equal to Q, P' is completely determined by the pair of points P1, P2. Hence, the same line Q, P' is obtained by replacing P3, P4 by any other pair of points on the conic collinear with P and distinct from P1, P2. This proves Theorem 13. Theorem 13' is the plane dual of Theorem 13. Definition. The line thus associated with any point P in the plane of a conic, but not on the conic, is called the polar of P with respect to the conic. If P is a point on the conic, the polar is defined as the tangent at P. Definition. The point thus associated with any line P in the plane of a conic, but not tangent to the conic, is called the pole of P with respect to the conic. If P is a tangent to the conic, the pole is defined as the point of contact of P. Theorem 14. The line joining two diagonal points of any complete quadrangle whose vertices are points of a conic is the polar of the other diagonal point with respect to the conic. Theorem 14 prime. The point of intersection of two diagonal lines of any complete quadrilateral whose sides are tangent to a conic is the pole of the other diagonal line with respect to the conic. Proof. Theorem 14 follows immediately from the proof of Theorem 13. Theorem 14 prime is the plane dual of Theorem 14. Theorem 15. The polar of a point P with respect to a conic passes through the points of contact of the tangents to the conic through P, if such tangents exist. Theorem 15 prime. The pole of a line P with respect to a conic is on the tangents to the conic at the points in which P meets the conic, if such points exist. Proof. Let P1 be the point of contact of a tangent through P, and let P2, P3 be any pair of distinct points of the conic collinear with P. The line through P1 and the intersection of the tangents at P2, P3 meets the line P3, P2 in the harmonic conjugate of P with respect to P3, P2. Theorem 9 corollary. But the line thus determined is the polar of P. Theorem 13. This proves Theorem 15. Theorem 15 prime is its plane dual. Theorem 16. If P is the polar of a point P with respect to a conic, P is the pole of P with respect to the same conic. If P is not on the conic, this follows at once by comparing Theorem 13 with Theorem 13 prime. If P is on the conic, it follows immediately from the definition. Theorem 17. If the polar of a point P passes through a point Q, the polar of Q passes through P. Proof. If P or Q is on the conic, the theorem is equivalent to Theorem 15. If neither P nor Q is on the conic, let P1 be a line meeting the conic in 2 points P1, P2. If one of the lines, P1Q, P2Q, is a tangent to the conic, the other is also tangent. By Theorem 13, the line P1, P2 equal P1P is then the polar of Q, which proves the theorem under this hypothesis. If, on the other hand, the lines P1Q, P2Q meet the conic again in the points P3, P4 respectively, figure 59, the point P1, P2, P3, P4 is on the polar of Q. Theorem 14. By Theorems 13 and 14, the polar of P1, P2, P3, P4 contains the intersection of the tangents at P1, P2, and the point Q. By hypothesis, however, and Theorem 13, the polar of P contains these points also. Hence we have P1, P2, P3, P4 is equal to P, which proves the theorem. Corollary 1. If two vertices of a triangle are the poles of their opposite sides with respect to a conic, the third vertex is the pole of its opposite side. Definition. Any point on the polar of a point P is said to be conjugate to P with regard to the conic, and any line on the pole of a line P is said to be conjugate to P with regard to the conic. The figure obtained from a given figure in the plane of a conic by constructing the polar of every point and the pole of every line of the given figure with regard to the conic is called the polar or polar reciprocal of the given figure with regard to the conic. A triangle, of which each vertex is the pole of the opposite side, is said to be self-polar or self-conjugate with regard to the conic. Footnote. It was by considering the polar reciprocal of Pascal's theorem that Briançon derived the theorem named after him. This method was fully developed by Poncelet and Gourgon in the early part of the last century in connection with the principle of duality. Corollary 2. The diagonal triangle of a complete quadrangle whose vertices are on a conic, or of a complete quadrilateral whose sides are tangent to a conic, is self-polar with regard to the conic. And conversely, every self-polar triangle is the diagonal triangle of a complete quadrangle whose points are on the conic, and of a complete quadrilateral whose sides are tangent to the conic. Corresponding to a given self-polar triangle, one vertex or side of such a quadrangle or quadrilateral may be chosen arbitrarily on the conic. Theorem 17 may also be stated as follows. If P is a variable point on a line Q, its polar P is a variable line through the pole Q of Q. In the special case where Q is a tangent to the conic, we have already seen, Theorem 12, that we have the pencil of points P is projective with the pencil of lines P. If Q is not on Q, let A, figure 60, be a fixed point on the conic. A, the tangent at A, X, the point distinct from A, if AP is not tangent, in which AP meets the conic and X the tangent at X. We then have, by Theorem 12, the pencil P is perspective with A pencil X, which is projective with A pencil X, which is perspective with Q pencil AX. By Theorem 13, AX is on P, and hence P is equal to Q AX. Hence we have pencil P projective with pencil P. If P prime is on the point PQ, this gives pencil P projective with pencil P prime. But since the polar of P prime also passes through P, this projectivity is an involution. The result of this discussion may then be stated as follows. Theorem 18. On any line not a tangent to a given conic, the pairs of conjugate points are pairs of an involution. If the line meets the conic in 2 points, these points are the double points of the involution. Corollary. As a point P varies over a pencil of points, its polar with respect to any conic varies over a projective pencil of lines. Definition. The pairing of points and lines of a plane, brought about by associating with every point its polar and with every line its pole with respect to a given conic in the plane, is called a polar system.
Projective Geometry, Volume 1, This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.